Hi guys, today we're going to learn about one of the most important things in calculus, which is the fundamental theorem of calculus. The other day we used geometry to evaluate integrals such as the integral from 2 to 4 x plus 1 dx. So today what we're going to do is we're going to connect this idea with what we know about finding antiderivatives. Okay, so the first thing that we're going to do here is we're going to graph the equation y equals x plus 1. Why that one? Because that one is the integrand that you have over here. Okay, so that's why. Okay, so what we're going to do here, you want it from 2 to 4, okay, and then you draw this line at 2. You know that this is going to be what, 3, okay, so it's going to be somewhere here, and at 4 is going to be something around here, 5, okay. In addition to that, you know that that line has an intersect at 1, okay, so let me just draw it very beautifully here. So that's going to be your graph that you have. But what is the area under the curve that we want? The area under the curve that we want is from here to here, okay, so specifically here to here. And the area is going to look like this, right? You can see that it's the area that it's here, okay, so it's this area that we have over here, okay, that it looks like a trapezoid, okay, do you see it? Okay, so how can we find this area that we have over here? Let me put that this is 3 and this one over here is 5, right, the output, okay. So, and this is your x and this is your y axis, okay. So if you want to find the area of that highlighted part, what you can do, and you don't remember, let's say, the area of the trapezoid, what you're going to do is you're going to split it as a rectangle and a triangle. The area of a rectangle is going to be base, which is 2, times height, which is 3. Do you agree with that? Plus the area of the triangle, which is 1/2 times base, which is 2, and the height, that is 2. Do you agree with that? So what you have here is that this is going to be 6 plus 2, which is going to be 8 units square. Do you agree with that? So now what we learned the other day is we learned how to find antiderivatives. You know that the antiderivative of x is going to be x squared divided by 2, and the antiderivative of 1 is going to be x, and then the plus c. Okay, that's what we learned. So now let's figure out how to connect the area with the antiderivative. Okay, so how are these related? Let's think about that. We can figure this out. Okay, what we're going to do over here is we're going to substitute the lower limit of integration, aka x equals 2, and the upper limit of integration, x equals 4, into your antiderivative. So if you substitute that, what do you have? You have 2, okay, squared divided by 2 plus 2, okay, that's what you have, meaning you have 2 plus 2, that's going to be 4, okay. Now if we do the same, okay, but with the upper limit, what happens? You have 4 squared divided by 2 plus 4, right? And this is going to be equal to, what's that, 8 plus 4, which is 12. Do you agree with that? So this is beautiful. What could we do, okay, to get the results that we found above using geometry? So you're like, oh, I can do 12 minus 4 and I get my 8. Do you agree with that? So you can see that that's what we have. And it turns out that this is always true, okay? This always works. This is what we call, this is the idea of the fundamental theorem of calculus, and we're going to see more in the next example. So what are the steps to find this area? Step 1, you are going to find the antiderivative, okay? You are going to, compute the indefinite integral. Then after that, you are going to substitute the upper limit, okay, into the antiderivative, and then the lower limit of integration to the antiderivative, and then you're going to subtract them, upper minus lower, okay. This is what we call as the fundamental theorem of calculus. As you can say, it's fundamental because it relates the two important ideas of calculus, derivatives and antiderivatives. Now we can find the area bounded by a graph and the x-axis for graphs in which we cannot use geometry. So this is amazing, okay? Now let's try on the next problem. Please note that you would not be able to find the value by geometry because this is a quadratic function, which you know that it's going to be a parabola, and a parabola is not a circle, it's not like a rectangle, it's not a triangle, okay? So you know that it's a curvy figure, very user-friendly, but it's not as easy to find the area. So what are you going to do here? You are going to compute the antiderivative first, so it's going to be 3x cubed divided by 3, Okay, what you're going to do here, and the notation that we can use, you can put brackets from 1 to 2. You are indicating the reader that you are going to plug the 2 on the 1 eventually, and then you cancel the 3's. Okay, so you can plug the 2, right? So we're going to have that it's going to be 2 here, okay, that it's going to be cubed minus 1 cubed. Do you see it? Okay, so now we're going to do this operation. You know that it's 8 minus 1, okay, 8 minus 1, which is 7. 7 units squared. So that is what you have as the area between 1 and 2 under the curve 3x squared. Do you see it? Now, let's write formally the fundamental theorem of calculus now that you can see that it's very user-friendly. Okay? So what the theorem tells you, if f is continuous on an interval ab, then what you have is the integral from a to b f prime, please note prime, of x dx is going to be equal to f of x. Okay, and this is going to be evaluated from a to b, and this is going to be equal to f of b minus f of a, and that's what the fundamental theorem of calculus tells you. Isn't this beautiful? So we're going to keep using this, okay, because it's super important, so you can see how simple is this situation, because you already know how to find indefinite integrals. This is just plugging numbers into the indefinite integrals that we had before. Okay, so let's look at this one, the integral from 1 to 2 x squared plus 3 dx. So what are we going to do here? First, you compute the integral 3x power 3 divided by 3, and then plus 3x, okay, and then you indicate the reader that you are going to plug what? 1 and 2. Okay, so what's the next step here? The next step is you are going to plug the 2, right? So you plug the 2, so 2 power 3 divided by 3 plus 2 times 3, you can do that, 6, okay? So you have this equation, then minus, okay, all of this, okay, because I plug the 2, minus, and then I plug the 1 cubed divided by 3 plus 3, okay, because 3 times 1 is 3, so you have that situation. Cool. Okay, so after that, what are we going to do? You know that it's 8 over 3, right, plus 6, okay, then you have that it's minus 1/3 minus 3, okay, and you do these operations, right, and you have that this is 16 over 3. Cool. So unit square, that's the area between 1 and 2 under x squared plus 3. Isn't that beautiful? Okay, let's do another one. Okay, so this should give you bias of indefinite integrals. So this one, what are we going to do when you have a situation like that? Okay, so first you are going to make it, okay, integral friendly, let's call it that way. Okay, so you have integral friendly this situation, right, dx. Okay, if you still don't see it, don't worry. Okay, we're going to make it integral friendly. So you have x power, what's that? 1/2 minus 4x power negative 1/2, and all of this dx. Now, do you see it integral friendly? Hopefully you do. Okay, so now what are we going to do? We integrate. Okay, so you have that it's x to the power of 3/2 divided by 3/2, okay, and then minus 4x power of, what's that? 1/2 divided by 1/2. Okay, all of this is going to be evaluated from what? 1 and 9. Okay, so what are we going to do next? Okay, do you agree that for both? Okay, so what can we do here? Okay, what we can do is several things. We can just, I'm going to put 2 over 3, and I can put x to the power of 3/2 minus, okay, and you have 8 square root of x if you want, and then you plug the 1 and 9. Okay, so what happens next? You are going to replace, okay, so you're going to put the 9 there. Okay, so you have this, and then you have 9 to the power of 3/2 minus 8 times 3. Okay, so that's your first part, minus, and then you plug the 1. Okay, so 2/3 minus 8. Do you agree with that? Yes. Okay, and then you have that this is going to be equal to 4 over 3. Okay, yes. Happy? Okay, so we have this. Okay, so let's move on to more examples so you can see that it's very, very user-friendly. So this one, oh no, we have trig functions. No worries, remember that one is in your formula sheet, so we already know that what's the integral of secant square, you know that it's tangent. Okay, so you're like, okay, user friendly. So you're like, I can integrate that directly. I know that it's going to be my tangent of x, that it's not that bad because we know that it's sine over cosine. Worst case scenario, that if you forgot your unit circle in the tangent, you can use it in sine and cosine. Okay, but here then, what do you have here? Do you agree that you have tangent of pi over 4 minus tangent of 0, which is great. Why? Tangent of pi over 4, you know that it's 1, and tangent at 0, it's 0, so this is going to be 1 unit square. Isn't that beautiful? So something that looked very bad, actually it's not. Okay, so the trig functions, sometimes they are your friends. In this case, they are. Okay, so let's look at this one. This one is a little bit more interesting. If you remember, when you have absolute values, it's a little bit more interesting. Why? Because technically speaking, if you remember from algebra 2, an absolute value is a piecewise function. Okay, so what you have here, you need to note something. Here we have that the absolute value of 2x minus 1, that's going to be a piecewise function. Okay, the first piece is going to be the one that you see, 2x minus 1. And the other piece, what's going to be that? That's going to be negative 2x plus 1. Do you agree with that? Why? Because you do know, okay, that you are going to have like a B situation. Now, how can we find the pseudo vertex of this absolute value? You know that if you equalize this to 0, you are going to have that it's 1/2. So the 1/2, let's say that it's here, okay, and if you see it, how I got that one, because I equalize this to 0, so you have that x is equal to 1/2. That's how I know that the pseudo vertex of the absolute value is there. Okay, so what do you have from here? Since you know a lot of properties of the absolute value, you know that the absolute value, if let's say that here is 1 and here's another one, okay, because it's symmetric with respect to the actual pseudo vertex that you have with the absolute value, you have something like this. Do you agree with that? That is your function. If y is equal to absolute value of 2x minus 1, that would be the graph. Yes? Okay, so what you have is that this happens for which one? This is for x when it's greater or equal than 1/2, and this is going to be x when it's less than 1/2. Okay, why? Because this is negative, the slope is negative, this one is positive. Okay, that's how you know. Okay, now let's look at the area that they are asking. What area they are asking? They are asking from 0, okay, which is here, up to 3, that it's somewhere here, right? Let's say that it's here. Okay, so what are we going to do here? You have the situation, so the area that we want is this one, this mini triangle, and this bigger triangle. So you have options, right? You can always use the triangle properties and compute it, but whenever you try to do an integral, you cannot do the integral as it is. What you need to do is you need to split the integral. Why? You have 2 pieces, so you need to be very careful. Both pieces are over the x-axis, so you can see that here's the x-axis. So I need to split my 2 integrals where? At 1/2. Why? Because I'm using this line for 0 to 1/2, and I'm using the other line from 1/2 to 3. Do you see it? So what you have here is the integral from 0 to 1/2 of what? Which one of the 2 are you using? You're going to use the negative, so it's going to be negative 2x plus 1, okay, and all of this dx. And then you're going to have plus the integral from 1/2 to, what was it, 3, and then you're going to use the positive one, 2x plus 1 dx. Do you see it? Then you are going to integrate the situation, right? You integrate this, so what do you have here? You have that it's negative x squared plus x, okay? And all of this is going to be evaluated from 0 to 1/2. That's the first integral. And the second integral that you have, plus, okay? What do you have? It's going to be x squared, okay? And this one, excuse me, that one, it shouldn't be plus. This one should be minus, okay? Okay, because I had this, okay? So that should be minus x. And then it's going to be from 1/2 to 3. Do you see it? Now, what are you going to do here? You're going to plug them in. So, if you plug the 1/2, what's going to be that? You have that this one is going to be negative 1/4 plus 1/2. Okay, you have a bunch of zeros, so I don't even put them. Okay, do you agree with that? Then this one over here, what do you have? You're going to plug the 3. Okay, so what's that? 9 minus 3. Okay, that's your first chunk. Then you have that it's going to be what? Parentheses 1/4 minus 1/2. Okay, and then what? You close it there, and what do you have here? Okay, you combine all of the situation, right? And we have that this is 13 over 2 unit square. Do you see it? Okay, let me box this apart so you don't confuse that part with my integral. Okay, so that's going to be my final answer. Cool. Okay, so for this example, you have the integral from -1 to 3, absolute value of x squared minus 4 dx. Again, you have an absolute value. So let's figure out what to do with this absolute value. Okay, so the first thing that you're going to do here is you are going to have your absolute value here, and you're going to split it, okay, as a piecewise function. So the first piece and the most natural to think about is this one. The other piece is going to be negative x squared plus 4. Do you agree with that? Now, the situation is when we use this one, when we use this one. So, do you agree that this one, okay, it's kind of like a parabola facing up, right? But the issue that we have here, since it's shifted 4 units down, okay, what you have is your parabola without the absolute value. Okay, so it would look like something like this. If this is, let me measure it here. Okay, so if this is 2, okay, and this is, well, this is -2, right? And this is 2, okay? Your parabola would look something like, and this is 4, right? This is -4, okay? Your parabola would look like something like this. Do you agree with that? But what the absolute value is doing to this graph? The absolute value, what it's doing is making this part positive. Do you agree with that? So if I reflect this one here, okay, the 4, and then I draw my absolute value here, okay, that's what the absolute value is doing to this piece. Do you see it? So it's very beautiful. Okay, you can see there the reflection, how the absolute value is affecting the original parabola. So you can see that we have this piece. Okay, that's the graph that we have, this being x and this being y. Isn't that beautiful? Now, what are they asking? They want, okay, a very crazy area. What area they want? -1, which is going to be this shaded region that it doesn't have a shape, up to what? Up to 3. So you want all of this also, and then you want a little chunk of this. So as you can see, this is not like in the form of a triangle, nor in the form of a semicircle, because it's a parabolic situation here and here. So it's very problematic. Okay, so now let's go over the domain. This part, when are we going to use this situation? Okay, the positive. Pretty much everywhere from -infinity to -2. Do you agree with that? Okay, so we're going to use it there. Union to infinity. Do you agree with that? That's when we are using this part and this part. When are we going to be using, okay, this one? This one is when your x is in between -2 and 2. Okay, why? Because it's the one that it's facing down. You know that if the negative leading coefficient, we have negative leading coefficient in the quadratic, then it's facing down. So you can see here how it connects to algebra 2. Cool. Now that we can see the area that we want, and we can see that it's problematic, what can we do again, following the idea from the previous problem? We need to split this area into 2 pieces. This piece that we have here, okay, and the piece that it's over here. Okay, do you see it? So this piece that it's facing down, you know that from -1, right, to 2, what piece are we going to use? The negative. Okay, negative x squared plus 4 dx. Why? Because the parabola is facing down. Then the parabola switches up here, okay, to the original, this one. Okay, so you have plus integral from 2 to 3, okay, of x squared minus 4 dx. Do you see it? Now, what are we going to do here? What you're going to do here is you're going to have negative x cubed divided by 3 plus 4x. Okay, you are going to evaluate these two from -1 to 2, and then you find the integral of that, which is x cubed divided by 3 minus 4x, and then you integrate from 2 to 3. Okay, then what are you going to do here? You plug them in, right? So you have that the 2 to the power of 3, that's going to be what? That's going to be -16. Okay, so negative 16, no, that's not negative 16, that's going to be 2 to so what do you have that it's that one? It's going to be, yes, over 3, okay, plus 11 over 3, okay, plus, okay, and then you have that it's negative 3, okay, plus 16 over 3. Do you see it? Okay, so I kind of like did it disorganized, but sort of, okay. So then we have that this is going to be 34 over 3 units square, and that's pretty much it. Okay, so be very careful when you have absolute values. Make sure that you are always taking care of when you are intersecting the x-axis, because that will impact how you compute your integrals and the order that you have over here. Make sense? So I hope that you find this video helpful. If you have any questions, please remember to write them in the comments, and I'll see you later. Bye.